very much. So let me begin by stating three theorems, and I will make my best to prove them all. Probably I will be able to prove the first one entirely, the second one at 80%, and the third one maybe 40%. But I will at least give the structure of the proof in each of the theorems. So the first theorem is due to Mann and Su, and it states the following. Suppose that X is closed and connected, a closed and connected manifold. Then there exists a constant C such that for any prime P and any natural number R, for which the product of R copies of mu P acts effectively on X, we have that R is not bigger than C. Okay? So these groups in the context of finite group theory are usually called elementary P groups, and R is usually called the rank. So what this theorem states is that if you fix a closed manifold, connected here is just to simplify the argument, but it's valid for non-connected manifolds in general. Then there is a bound on the rank of all elementary P groups acting on that manifold, and this bound is independent of the prime. That's an important issue. Yes, but this is highly non-trivial. If this is, you say finite abelian.
No, just finite.
Okay. Well, let me say, if you had meant finite abelian groups, then for sure this gives a bound on the number of generators, and this is elementary. For non-abelian groups, this is also true, but this requires the classification of finite simple groups. So this is a yes.
But sorry, it doesn't follow from this question theory.
I mean, if you are given an arbitrary finite group, you should not expect to have elementary P subgroups that are really big inside your finite group. So using elementary arguments, it's very hard to deduce anything significant about finite groups out of this information. But you can do it, but I mean, using highly non-trivial theorems.
What was the finite theorem last time?
Excuse me?
What was the finite theorem last time?
I don't understand.
Last time. What was the finite theorem?
Okay. So you can prove that you can prove using the Mann and Su theorem that if you fix a closed manifold, then there is an upper bound on the number of generators for any finite group acting on your manifold.
But not on the cardinality.
No. In general, I mean, if you have a manifold which supports an action of the circle, for example, you can't pretend to find any restriction on the cardinality of the groups.
I asked you about the theory from the previous lecture, or I asked you about the theory from the previous lecture.
Yeah, okay. Yes.
What was it specifically?
It was. Yes, manifold supporting a hyperbolic. Yeah. Okay, so this is the theorem of Mann and Su. The second theorem refers to so-called hypertoral manifolds. So a connected n-dimensional manifold X is hypertoral if there exists n, so n is the dimension, one-dimensional cohomology classes whose product is non-zero. Okay, so in particular, this implies that the nth dimensional cohomology group is non-zero, which implies that X is closed and orientable. Okay, so now I have this theorem. If X is an n-dimensional hypertoral manifold, then there exists a constant C such that for any finite group G acting effectively on X, we have the following two statements, depending on the Euler characteristic of X. If the Euler characteristic of X is non-zero, then G has at most C elements, and if the Euler characteristic is zero, then the claim is that there exists a subgroup G naught of index at most C, and this group can be embedded in S1 to the n, so in the n-dimensional torus. Okay? So, this theorem generalizes to higher dimensions. In the first statement, the theorem for surfaces of genus 2 or more, and the second statement, the theorem for surfaces of genus 1. Okay? But I should say that, of course, the first statement does not contain the statement that I proved yesterday. So yesterday I also proved a generalization of the theorem for surfaces of genus 2 or more, but the theorem of yesterday, for example, applies to odd-dimensional manifolds, provided they support hyperbolic metrics. But odd-dimensional manifolds always have vanishing Euler characteristics, so this statement here does not apply for odd-dimensional manifolds. Okay? Let me make you observe that, for example, the first statement implies that if you take the connected sum of two copies of torus of dimension 2n, then this does not support an effective action of the circle. Okay? And the reason is that this is a hypertoral manifold. In fact, if you take any closed manifold and you make connected sum with a torus, what you get is an example of hypertoral manifold. Okay, because
You just get the classes from the topics.
excuse me.
You just get the desired classes from
Exactly. You have a map from. Well, let me put it M here. You have a map to Tn which collapses this summand here, and then you pull back standard generators of the first cohomology of Tn.
So, in general, if you have subjective finite cover of totals, then the variety is like this, right?
Exactly, it's hypertotal.
Is it equally or
Oh no.
you have a subjective cover of totals?
Oh yes. Well, not yes, surjective and of non-zero degree. In fact, yes. I will prove this. Yeah. Okay, and finally, third theorem. Suppose that X is a closed and connected manifold with non-zero Euler characteristic. Then there exists some number n such that for any finite group G acting effectively on X, there is an embedding of our group inside GL and C. Okay? And this generalizes the statement for finite group actions on the two-dimensional sphere. Okay? Sorry?
Is it the same, so if you have this embedding, is it the same final example which is the totals?
This, yes. Yeah, that's one of the. Well, I mean, I wrote it this way because this is roughly the same statement that I wrote for S2 the first day. But yes, when I will talk about this theorem, the first thing I will say is that this is equivalent to Jordan property. Yeah, roughly. I mean, it is equivalent to the existence of an abelian subgroup of G of controlled index, and also with a bound on the number of generators, which need not be the dimension of the manifold. In the theorem for hypertoral, yes. And X is n-dimensional, and you have the embedding inside S1 to the n, which implies that G naught can be generated by n or less elements. Okay? Well, so these are the three theorems I would like to prove today. Let me begin with the theorem of Mann and Su. The first step consists of proving that you can restrict attention to free actions. Okay? And this is justified by the following construction. Let M be a connected manifold. And now I'm writing M on purpose to avoid confusion with X. And let H be a Riemannian metric on M. Okay? Then I define FH of M to be the bundle of orthogonal frames, H orthogonal frames on M. So this consists of these tuples. So I assume that n is a dimension of the manifold. So X is a point of M, and V1 up to Vn is an H orthogonal basis of Txm. Okay? Well, this has a natural topology, and in fact, it has a natural structure of a smooth manifold. Okay? I will be interested in that manifold being connected. And the way it is defined, it's connected only if M is not orientable. Okay? So, if M is orientable, then we fix an orientation and require that the basis V1 to Vn is an oriented basis. Okay, and then if we take this precaution, then this is connected in both cases. Okay, this is a consequence. Exactly, yes. Yeah. This is a consequence of the fact that SON is a connected Lie group. Okay? Well, now, second thing is that for any two Riemannian metrics, on M, you have a map, a well-defined map from FHM to FH prime of M. Well, I didn't write it, but let me write it to stress the fact that this is a smooth manifold in a natural way. Okay? Okay. Now, we can define a map from FH to FH prime using Gram-Schmidt orthogonalization process. Okay? Is that clear? I mean, you have a canonical process. If you are given a basis and on an Euclidean space, you have a canonical way to transform it into an orthogonal basis, and the procedure depends smoothly on the initial basis. Okay, because it consists of dividing by the norm, and this norm is always non-zero, and adding perpendiculars and so on. They are always smooth operations. Sorry? What do you mean invertible?
I mean that you have, like little manifold, you have two bases in a vector space.
Yes.
And you take one to be orthogonal with respect to the other form, to the other way around, you don't get.
That's right, you're absolutely right. So if I understand you properly, what you mean is that if you have one basis, I mean two metrics, you pass one, take an orthogonal metric an orthogonal basis in the first metric, apply Gram-Schmidt to go to the second, and you gain and apply Gram-Schmidt, and you don't get the initial one necessarily. That's true.
So in particular, if you have a map from here to there, from there to here, but then...
The composition is not the identity, but this is a diffeomorphism. Okay? Okay? And the reason why this is a diffeomorphism is that although the composition of this map with the other natural map to FHM is not the identity, it is a diffeomorphism of FHM, because again, for the same reason that Gram-Schmidt depends smoothly on the initial data, basically. I mean, okay, the consequence is that as a smooth manifold, FHM is canonically associated to M. Okay. Now we have the following lemma. Suppose a finite G acts on M effectively. Okay? Then we might take a J invariant Riemannian metric on M, and it turns out that the action of G on M lifts in a natural way to an action on FHM, which is free. Okay, let me prove this. First, how the action is defined, I guess, is clear. You use the differential map. Okay? I mean, I'm interested on having a compact manifold. Okay? No, I need not be free. No, because if there are fixed points, and you take any tangent direction to a submanifold of fixed points, then this tangent direction will be preserved. Do you see what I mean?
What do you mean by orthogonal? Do you mean orthonormal?
I always confuse orthonormal. Well, yes, orthonormal. Orthogonal means. Yeah. Orthonormal should be. Yes. Sorry. Orthogonal, orthonormal. Yeah. Okay. So orthogonal is that they are pairwise perpendicular, but not necessarily of modulus 1. Okay. Orthonormal. Okay. Okay, so the lift is defined using the differential of so if you have an element G of the group and you have a point in the frame of in the manifold of frames, then well, you make G act on X, no change here. But then when you take the differential of phi G at the point X, acting on V1, and so on. Is that clear? Okay, so remember, phi G denotes the diffeomorphism of X with itself given by the action of G. Okay? Well, now let me define sorry. Take an element and let U be the set of points in FHM that are fixed by this element. Okay? I claim that U is open and closed. That it is closed, it is clear, because it is given by this equality involving continuous functions. Okay? So there is no need to say anything else. Let me prove that it is open. Suppose you have a point that is fixed by H. Okay. Now the exponential map with respect to H at the point X, which goes from here to here, this map is equivariant with respect to the group generated by G. Let me denote it this way. Okay. Right? Now, by hypothesis, G acts trivially here. Okay? And this implies that in the neighborhood of X, on which this is a diffeomorphism, the action of G is trivial. Let me write it carefully. There exists a neighborhood of 0 in the tangent space such that X restricted to W is a diffeomorphism and furthermore this, which I may call Z, and Z is a neighborhood of little x. Okay? The conclusion is that G acts trivially on Z, okay? Because I insist, G acts trivially here. Because by assumption, we have a basis of this vector space on which the action of G is trivial. So by linearity, the action on the entire vector space is trivial. So. Okay. Well, G acts trivially on Z, and Z is the neighborhood of X. This implies that G acts trivially on any point of the frame bundle over Z. Okay. Let me say that is an open neighborhood. Let me take all neighborhoods of the open to. Sorry. So pi denotes the projection. Okay. Yes. The condition for you to be no, I'm taking an arbitrary point of view. Okay, let me give the name P. Okay, and the conclusion I will reach is that U contains a neighborhood of P for any point P of U, and this implies that U is open. Okay. So this is a neighborhood of P. Okay, the conclusion is that U is open. It is also closed, and the frame bundle is connected. So either U is the empty set or the total space. But if U is the total frame bundle, this implies that the element little g acts trivially, and this contradicts the hypothesis that the group is that the group action is effective. Okay? And this finishes the proof. Right? So, summarizing, I have associated to any closed manifold a new manifold, which is also closed, which is a orthogonal frame bundle for any choice of metric, and I have proved that any group that acts effectively on the first manifold acts freely on the second one. Consequently, if we want to understand, if we want to obtain restrictions on groups acting effectively on all manifolds, it suffices to prove restrictions on groups acting freely on all manifolds. Okay? In other words, to prove the theorem of Mann and Su, I can restrict to free actions. Okay? Not only effective, but free actions. Okay?
Presumably you use this lemma in the proof of the other two theorems as well.
Sorry?
Because if you are working just with a P torus, you can construct a much simpler manifold by just taking, say, a product with a torus of X. in this theorem, G is not arbitrary, it's just the product of
Here.
right?
Yes, yes.
You can multiply your manifold with the forms. The product of this one can be this X3. To get also, maybe you need something else.
The problem is that when you say you multiply by a torus, you probably are thinking of an r-dimensional torus, okay? But then you are making a construction that depends on the group. And
yeah, but just depends on R.
Yeah, but I don't want, I mean, my construction doesn't depend on any choice of group.
Yeah, that's what I asked.
Yeah.
Presumably you need, you would like to use it in other.
No, but I don't think that multiplying by an r-dimensional torus would work in this case, because you want to have an a priori bound on R.
It doesn't depend on R.
Exactly. I mean, when you look for restrictions on finite group actions, you can do whatever construction you want on your manifold, but it must be independent of the choice of a group. Because if it depends on the group, then you are already prescribing the group.
So just suppose you want to serve with P with all of 100, then you have to multiply the 100 with groups. For other logic, multiply by 100.
And the constant, I mean, it might depend on the dimension, right? I mean, if the
constant C, yes. So
it might depend, for example, on the x. It depends on the x itself, for example, on the dimension.
Yes. That will be clear. Exactly. Yes. Yeah. I mean, the constant I will find will depend on the Betti number. Basically, well, on the cohomology, on the integral cohomology of x. Okay. Okay, so let's prove Mann and Su theorem. So we can assume, so it suffices to consider free actions. Okay, now let me define beta j to be the maximal over the primes p of the jth Betti number of x with coefficients in Z mod p. Okay, this is always a finite number because x is supposed to be closed, so the cohomology is finitely generated. Okay. Now suppose that P is a prime and R is a natural number, and this guy acts freely here. Okay? Then the equivariant cohomology for this action is going to coincide with the usual cohomology of the quotient, because the action is free. And this is going to vanish. No. It is definitely finite because the manifold is closed. Okay? Of course, this may vary with P if there is P torsion. Okay, but whatever torsion there is in the cohomology, it is supported in a finite collection of primes, and it's finite. Okay. Now, now this cohomology vanishes if k is bigger than the dimension of x. let's call it n. Okay. Well, now we have a spectral sequence converging to the equivariant cohomology. Sorry? Exactly, yes.
And this is the new manifold which depends only on x. Okay, but you're talking about the action on x. Yeah, but there must be some force that depends on x, and how it depends only on x.
Yeah, that's the reason why I was working with m and not with x, to avoid confusion. So, okay. Now we have sorry, and this is with arbitrary coefficients. Sorry, I didn't say it, but well, I use this notation for integral cohomology, but this is true, of course, for arbitrary coefficients. Yeah, okay. But I'm going to work with Z mod P coefficients. Okay. Now, here's the strategy I'm going to follow. So I'm going to look at the entry in the bottom line corresponding to n plus 1. Okay? So this stays in the position n plus 1, comma 0. Okay? And so this is this is supposed to be a picture of the second page. Okay? And now, as you know, as you pass from one page to the other, elements in the spectral sequence decrease in size. So I'm working with Z mod P coefficients, so these are vector spaces and the sizes that I mentioned, okay? So the size of the terms decrease every time. But if you look at this square, since all differentials departing from this square are 0, because on the negative height everything is 0, okay? Then the only way this guy can eventually die is by the contribution of differentials coming from these positions, right? Okay? In the first page, you will get a differential from this guy to here. In the third page, you will get a differential, well, not from this piece in the second page, but from the piece in the third page, which is a subquotient and hence has smaller size and so on. Okay? So, if we want this element to be 0 after a number of pages, the dimension of this guy has not to be at most the sum of the dimensions of these guys. Of course, right? For this guy to vanish, infinity. We need the dimension of, 0. to be okay? So we need to control these dimensions. And this dimension will be able to compute exactly as a function of R, not of P. And for these dimensions, so these are the dimensions of these guys, we will use what I proved yesterday, namely that you can bound the dimension by the, well, I proved something for mu p, but I mean, it's what I explained works perfectly on any base, okay? And so we will have an upper bound for this guy in terms of the dimension of the ith cohomology of this guy with z mod p coefficients multiplied by the dimension of this guy, okay? Now, of course, well, let me now compute the cohomology of this classifying space. This classifying space can be identified with the product of R copies of B mu P, okay? And we can compute the cohomology with Z mod P coefficients using QNet, because Z mod P is a field, okay? By QNet, the dimension of H K of mu P R with coefficients in Z mod P is equal, well, you have to, sorry? Yes, yeah. At the end is the same thing. I mean, if you think of group cohomology, the group cohomology coincides, but this is more consistent with. Okay, so what QNet, we know that this naively behaves as a polynomial. It is not a polynomial algebra, the cohomology, yeah, but it has one piece in each dimension. So at the end, this dimension is going to be the same as the dimension of the kth piece of a polynomial ring in R variables, okay? And so this is this right here, okay? But I mean, by QNet and by the computation of the cohomology of B mu P, which we did the first day, okay? So let's give a name to this expression. Let's call it BRK, okay? And now, so we need the following. So this, of course, in the bottom line, since the manifold is connected, this is the trivial local system Z mod P. So what we have is the cohomology of the classifying space. Okay. So this dimension here is precisely this one. Okay. Let me set k equal n plus 1 to simplify. So we have B R K. Okay. Now this should be at most this guy here, and now we can bound this as follows. So we combine this by beta j b r comma I. Okay, so this is the, I'm using here that lemma that I proved yesterday when proving the first theorem of Smith. Okay? Well, we are almost done because now this is what we know is that we have these numbers, they are fixed a priori, okay? And now what we want to prove is that if R is too big, then this inequality cannot hold, okay? So how can we justify it? Well, the idea is that this is, for a fixed k, this is a function which grows with R, right? Sorry? Exactly, that's right, exactly. This is a polynomial, exactly. You can think of these in terms as a polynomial but be careful. We are moving R, so we are moving the degree of the polynomial. Okay, so. Oh yes, of course. Yeah, that's yeah. Thank you. Yeah, exactly. Oh, that's that's a neat way of proving this. So this is a polynomial of degree k. Well, no, but these are also polynomials of degree k. No, yeah. No, we have to be a bit careful. Yeah, I think that if you apply the same trick here, you will also get polynomials of degree k. Yeah, but anyway, we can argue as follows. What we have is that BRK is equal to k plus R minus 1 factorial divided by k factorial R minus 1 factorial. And if you want to compare it with BRK minus 1, what we have is that this extra factor here divided by this one, and we get here BRK minus 1, okay? And this is always bigger or equal than 0, which tells us that this is this expression as a function of k is growing, and in particular, this is bigger or equal than k plus R minus 1 divided by k multiplied by B R I for any I bigger or equal, so at most k minus 1. In fact, the guys appearing here, the guys appearing here have I at most k minus 2, so my bone will be very far from optimal, but I'm happy with it. Okay, and now the thing is the following. We have that this guy is bigger than that, so if that equality holds true, then what we should have is k plus R minus 1 divided by k should be at most this, okay? You just apply this inequality for this and this, okay? And of course, this depends only on your manifold, and if R is too big, then of course this will not hold. Well, so this finishes the proof of the theorem of Mann and Su. Let me now prove the theorem for hypertotal manifolds. Okay, I will first talk about a result on actions which are trivial on cohomology. Okay, let's state it as a lemma. Suppose that M is a closed manifold. Then there exists a constant C such that for any finite group G acting on M, there exists a subgroup G naught of G such that the index of G naught is at most C, and G naught acts trivially on cohomology. Okay. Now, this is almost an immediate consequence of the following lemma due to Minkovski. Which says the following: for any n, there exists some k such that if G is a finite subgroup of G, L, and Z, then G has at most k elements. So there is a uniform upper bound depending only on n on the size of the finite subgroups of G, L, and Z. Say it again? Yes. And then a posteriori you get the same statement for any coefficient group.
But C depends on
But by the universal coefficients theorem, if the action is trivial on integral cohomology, it's going to be trivial with coefficients in any other ring. Now, Minkovski lemma can be proved with a simple observation. It is the following. You have a natural map from GL and Z to GL and Z mod 3 simply by reducing coefficients modulo 3. Okay, and this is a finite group, of course. Now the claim is that this natural map is injective when restricted to finite subgroups of GL and Z. And the proof of this statement is a nice exercise in modular arithmetic. It's an elementary statement. You have to do the following. Suppose you have a matrix here of finite order, okay? Now you assume that this matrix goes to the identity here. So this matrix is of the form identity plus 3 times a matrix with integral entries. Okay, then you have to prove that that matrix is actually the identity. Okay, and well, it's a funny exercise, so I left it to you. Now, so how far is Minkowski theorem from implying that lemma? Well, of course, I mean, if you have a general action of a finite group of M, on M, you consider the induced action on the cohomology. Okay, and the induced action will be given through a finite subgroup of the automorphism group of this ring, right? Now, if there is no torsion, then you can identify the automorphism group of this ring with the product of GL and Zs, where N is the dimension of each cohomology group. Okay? So in that case, Minkowski lemma immediately implies this lemma. If there is torsion, then you need to use the fact that the torsion is finite, and it's a simple argument that allows you to conclude that lemma here. Okay? So, okay, so this means that to prove, I mean, whatever statement we make referring to subgroups of controlled index of finite subgroups acting on a given manifold, you can assume that your finite subgroups are acting trivially on cohomology. Okay? And we're going to do that to prove the theorem 2. Okay? And what we're going to do is to, so we assume finite G acting on X, and we assume that the action is effective and trivial on cohomology. Okay, and now I'm going to define a smooth version of the Albanese map using precisely the classes. Okay, suppose that you have classes satisfying this, where N is the dimension of the manifold. Okay, for convenience, it will be useful to introduce the following notation. Suppose that this is equal to plus minus d times a generator of the nth dimensional cohomology. Okay, and I want D to be natural. Okay? Is that clear? So I associate a natural number to these classes. Okay, now, I'm going to take now smooth one forms representing these classes. So, suppose alpha E naught satisfies that alpha I is the cohomology class here. And of course, this is an equality in X with real coefficients, okay? But never mind. Good. Now, I'm going to make the average of the action of the elements of G on each of these forms. Okay, and I claim, of course, this one form is J invariant, but but I claim that it represents the same cohomology class as alpha I. And the reason is that the cohomology class of this guy is the same one as the cohomology class of this guy, because by assumption, the action of G on cohomology is trivial. Okay? So, this is one form which is J invariant, and the cohomology class it represents is again alpha I. And now I construct a map as follows. I choose a base point in the manifold and define big phi from M to R mod Z, R mod Z to the N, which of course I identify with S1 to the N, by sending phi x to okay, and this is what I call the Albanese. Is this appropriate, Kostia? This is the Albanese or the Abel-Jacobi? I always doubt. Albanese. Okay, so this is the Albanese map, but in the smooth setting. So the meaning of these integrals is the following. I take any path going from x naught to x, and I integrate along this path each of the forms. This is well defined only up to integers. Okay, that's why I land here. And the reason is that a priori there could be non-homotopic paths going from x naught to x, but any pair of non-homotopic paths, or any pair of paths whatsoever, can be combined to obtain a loop beginning and ending in x naught. Okay, and hence the ambiguity of this expression without the brackets is expressed in terms of integrals of the form A1 along loops beginning and ending in x naught. But A1 is a class that comes from the integral cohomology. So when you integrate along a loop, you get an integer. And that's the reason why this is well defined. Okay, now I claim that this that this map is J equivariant in a precise sense. So let's define a map psi from G to S1 to the N by setting psi of G equal to phi of Gx naught. Okay, then I claim that that phi of Gx is equal to psi of G plus phi of x. Okay, let me justify this. So let's look at the ith coordinate. Well, we can split this as this plus this. No, sorry, I don't want this, I want this. Okay, well, this is clearly psi of g. Okay, and now this is equal to the following expression. Here. Okay, so I'm applying the diffeomorphism phi of g minus 1. Remember, this is the diffeomorphism given by the action of g to the minus 1. Okay, to the entire integral. Okay, so the extremes of integration are multiplied by g minus 1, so we get x naught and x. Okay, and the form changes this way. But we know that this form is invariant, so this is equal to this, which of course is phi of x. Okay? Well, this implies that that psi is actually a group morphism. Okay, and now let's define G naught to be the kernel of psi. Okay, so that we have an exact sequence like that, and this is a subgroup of S1 to the n. Now there are two lemmas. The size of G naught is at most D. Okay, recall D is this class here. Okay? And second lemma, well, I think, no, this is a bad notation. Sorry. Let's call it G1, because otherwise, now this is not going to be the G0 of the statement. Sorry. Okay? Now, second lemma. Given A and B, there exists some C such that if you have an exact sequence of finite groups, say A, gamma, B, 1, and A has at most A elements, and B is abelian, generated by at most little b elements, then there exists a subgroup gamma naught with index at most C, and gamma naught is abelian, or let me put it in a more synthetic way. And there exists an embedding of gamma naught inside S1 to the power B. Okay? Well, and a third lemma, sorry. If you take any element G,
and gamma only injects to B, like to R.
S1 to the B. Okay, and the other lemma is that if G is an element that does not belong to G naught, then G acts freely on X without fixed points. Okay? Now I claim that these three lemmas imply the theorem too. Yeah, sure, sorry. I claim that this, sorry? Yes, thank you. Yeah, in the kernel, yeah. I claim that these three lemmas imply the theorem too. For example, suppose that X has non-zero Euler characteristic. We are assuming that the action of G on the cohomology of X is trivial. But then this implies by Lefschetz fixed point theorem that there is no element acting freely, right? So then lemma 3 is telling us that in that situation, G1 is equal to G. Okay? And then lemma 1 gives the bound on the size of the groups acting. Okay? If the Euler characteristic is 0, then we apply lemma 1 and lemma 2. Okay? Now, sorry?
In that case, G1 is G0.
No, in that case, you get this gamma 0, which is the G0. Yes. Okay, how about the proofs? Very briefly. Lemma 3 is almost obvious, because what does it mean that little g doesn't belong to G1? It means that it acts non-trivially on the torus, okay? By translation. But then if you have a translation of a torus, then it has no fixed point, right? So if we have this map from, M again, sorry, from X. We have this map from X to S1 to the N. And if you have an element of the group that acts here non-trivially and consequently has no fixed point, its action here cannot have fixed points because this map is equivariant, okay? And if it had a fixed point, then the image of the fixed point would be a fixed point here, right? And there are no fixed points here when you apply a non-trivial translation. Okay, so this justifies lemma 3. Lemma 2 I leave as an exercise. I mean, I will be happy to give details if anybody is interested, but it can be proved with very elementary group theory. You don't need to use any technology. How about this? Let me briefly give the idea. The fact is that the map phi, so we have this map phi from X to S1 to the D. Okay? Sorry, to the N. And so here the way we have constructed this the map implies the following. Suppose that A, theta, is a generator of this. Okay? Now if you pull back the class here, and where theta is in the ith position, what you get is, well, plus minus alpha I. Okay? I mean, to understand this pullback, you only need to consider the ith coordinate of phi, then this is a standard fact. Okay? I mean, the fact that if you have the Albanese map for a one form and you pull back the generator of the cohomology in the circle, you get the cohomology class that was used to define the map. Okay? And now this implies that phi has degree D. Okay? So this answers your question. I mean, we have proved that we have this map to a torus of non-zero degree. And now how can we use this fact to prove this? Well, let X star be the set of points on which G acts freely. Okay? Now I claim that this has zero measure in the torus, the image. Okay? Well, let me not give details. I mean, this is a union of proper set manifolds. Okay, and then you can apply Sart's theorem to conclude that this has measure 0. Okay? So, away from this point, I mean, if you take any point in S1 to the n not contained in this image, then the action of G there is free. Okay? Now, let me say it in words, and so that I can devote 5 minutes to talking about that theorem. Now the thing is the following. You know that if you have a smooth map of non-zero degree, you can actually compute the degree taking a regular value, which exists by Sart's theorem, and then as it is a regular value, there is a finite number of preimages. Okay? For each preimage, you can define a sign depending on whether the map reverses or not the orientation. Now, the degree is equal to the sum of these signs, right? Okay, let me write this down, otherwise maybe it's not so clear. If this guy is regular for phi, then D, which is the degree of phi, can be computed by taking the sum over all preimages of y of the sign. Okay, so this is a standard formula in differential topology. Now the thing is that if G acts freely here. If G naught acts freely here, no, G1, sorry. Well, this means that it will permute the summands in this summation. Okay? We know that G acts cohomologically trivial in cohomology, and this means that it preserves the orientation in particular. So the action of G1 on this set preserves these numbers. Okay? Well, the conclusion is that this sum should be divisible by the cardinal of G1. Okay? Oh, sorry, sigma phi, more appropriate. And of course, this implies that the cardinal of G1 is at most D. Okay? This is more or less clear. And the thing is that you can assume that there exists some regular point on whose fiber G1 acts freely thanks to this. Okay? Well, this more or less concludes the proof. So what shall I do for theorem 3? I mean, maybe in 5 minutes I can give you the structure of the proof, or...
Well, maybe you can explain the structure.
Yeah, okay. Let me explain the structure of the proof of theorem 3. So, I will explain the 4 steps in the proof. Okay? First, suppose that this G denotes a collection of finite groups. We say that this G satisfies the Jordan property JCV, and this is slightly different from what we usually call Jordan property, but never mind. If for any element, say gamma, in the collection G, there exists an abelian subgroup which has index at most C, and which can be embedded in S1 to the C. Okay? Well, now an easy lemma applying to any collection of finite groups says that G satisfies GCD for some C and D. Okay, well, let's say there exist C and D such that G satisfies JCD if and only if there exists N such that sorry? Sorry. It's here. Sorry. Yeah, thank you. There exists some N such that any element, any gamma in this collection can be embedded in GL and C. Okay, but this is an elementary lemma. Okay, Now, second step. So this was step one. Define T of G to be the elements in G which have a normal silo, okay, such that the quotient is a prime power. The cardinal of the quotient is a prime power. Okay. In particular, these are groups whose cardinal is the product of two prime powers. Okay. But the condition is stronger than that because we require the existence of a normal silo. Okay. Now there is a theorem by myself and Alexandra Turull, which says the following: if J is closed under subgroups, so if you have any element of G, then all subgroups of that element also belong to G. Okay? Then for any D, there exists C such that G satisfies GCD if and only if there exists some constant which need not be the same one as this, such that T of G satisfies G C prime D. Okay? So if you have a collection of finite groups and you want to test whether it satisfies this property, then assuming that the collection satisfies this very reasonable property, it suffices to consider the subgroups which are of this form here. Okay? The proof of this theorem uses the classification of finite simple groups, so this is far from trivial. Okay, two more steps and finished. Let X be a closed manifold, and let G be the collection of finite subgroups of diff. Okay? So this certainly satisfies the condition of that theorem. Okay? Now, a theorem which is a refinement of that theorem states that we have the following. There exists some C and D such that G satisfies JCD if and only if, I don't know why I'm saying that, for anything. There exists C prime such that P of G satisfies G C prime D. Okay, so this P of G are simply the P groups. Okay, so this is a much more restricted collection than this one here. Okay, so when we are considering the collection of finite subgroups of the diffeomorphism group of X, which, by the way, is precisely the collection of all finite groups that act effectively on your manifold. I mean, a group acts effectively on your manifold if and only if it is isomorphic to a subgroup of diff. And last step is to check that if the Euler characteristic of X is non-zero, then this is true. Okay? Oh, this is P of G. Okay. Now, by Mann and Su theorem, it suffices to prove the existence of a constant C such that for any P group acting effectively on X, there exists an abelian subgroup such that this is at most C. Okay, abelian. Okay. So how do we prove that? There is a lemma, and with this I finish, that says the following: if the Euler characteristic is non-zero and X is closed, okay, and connected, then for any prime and any finite P group acting on X, there exists some subgroup of index at most the Euler characteristic of X, and such that gamma naught fixes one point at least. Okay, and then for any X fixed by gamma naught, we get an embedding of gamma naught inside GL and R. Okay, and now here, I'm really 10 minutes over the time. Here we can apply a classical theorem of Jordan, which states that if you have a finite subgroup of GL and R, this subgroup contains an abelian subgroup of index bounded above by a constant that depends only on n. Okay. Well, the proof of this lemma is rather elementary. You take an equivariant triangulation of X and you count orbits of simplices under the action of the group gamma. And you use the same trick that has appeared several times of divisibility. I mean, If you have a sum of powers of p and this sum is divisible by some power of p, then ignoring the powers of p of higher exponent, then what you get has also to be divisible by this power of p. Okay? Well, so I think it's good time to stop.